Cool. Today we're lucky to have Robert Lange, who is a fourth-year PhD student working on evolutionary meta-learning at the Technical University of Berlin. His work is funded by the Science of Intelligence Excellence Cluster and supervised by Henning Spreckler. He's currently working as a student researcher at Google DeepMind with the Tokyo team. Previously, he completed a Master's of Science in Computing at Imperial College London, a Data Science Master's of Science at Universitat Pompeu Fabra, and an Economics undergraduate at the University of Cologne. He also interned at DeepMind on the Discovery team and Accenture and maintains a set of open source tools, including the JAX libraries, evosax, Gymnax, and the MLE infrastructure, which I suspect we're all familiar with at this point. We're super excited to have you, and I'm going to mute myself and you can take it away from here.
Awesome. Thank you very much, Eugene, for that wonderful introduction. As already said, I'm Robert, and today I want to talk about two of my favorite topics, one being accelerated computation and JAX, and the other being evolutionary optimization. And the title of my talk is Discovering Black Box Optimizers via Evolutionary Meta-Learning. And before I get started, I have to say this is joint work with a set of wonderful co-authors and collaborators, including Tom Schall, Yutian Chen, Tom Zahavi, Valentin Talibat, Chris Liu, Satya Nothing, and Sebastian Flenner. And this was mostly work done during my previous internship last year at Google DeepMind. So before I get into technical details, many of you probably know this famous painting by Michelangelo, where we can see this magical biblical moment in which we have God, an old white man who's about to instill life into Adam, a young white man. And the beauty of this painting arguably arises from sort of this latent knowledge that when the two fingers of these two characters are going to touch, there's going to be the creation of life. And right now, we're arguably at a similar inflection point in the machine learning community, where there are many people who believe that we're very close to AGI, and the only thing that we have to do is scale large transformer models and gradient descent-based optimization, and eventually we're going to get there. And oftentimes people use the central nervous system and neuroscience or the brain as a motivation, right? So think of things like the reward prediction error hypothesis and the prefrontal cortex and meta-learning. But what if this whole sort of motivation and agenda is ultimately just a local optimum, and we're not going to get to that point just following and scaling this approach? One biological process of which we know that it has led to intelligence in many different diverse forms is biological evolution, right? So what I want to do today is not bash on gradient descent-based optimization, but instead just highlight or motivate sort of a call for more diversity and more diverse thinking when it comes to our own sort of meta research or meta science agenda. Okay, so this talk is not supposed to be an art history lesson, but instead I want to sort of talk about evolutionary optimization and meta-evolution as a tool to discover new algorithms. And I also want to talk a little bit about how software and accelerated computing in the form of JAX can help us do so. So on this very schematic slide, I hope to paint a picture of how the excitement of this talk is going to go. And now that I gave you this highly philosophical pitch, we're going to take a step back and look at what evolutionary optimization is, what the challenges are, and how JAX and an open source library called evosax that I maintain can help us do evolution on modern hardware and with sort of the benefits of all of that it brings. And then afterwards, we're going to talk about two papers that I wrote during my internship, and in the end, come back to more of a philosophical perspective. Okay. So before I get started, if you want to have a look at the slides, there's a TinyURL link called TinyURL Depot, where you can just sort of get to a Twitter thread, and this is going to point you to the slides, and then you have all of that to look at. So let's get started with just doing sort of a small background introduction to what black box optimization is. So I guess all of us are familiar with what white box optimization is, where we assume to have access to a function with some parameters which we're interested in optimizing. Let's call them x. And we assume that we have access to gradient evaluations or gradient computations of that function with respect to these parameters. And sometimes we even have access to the Hessian, but most commonly in deep learning, this is either computationally expensive or just a problem when it comes to memory or the accelerator. And then we can do gradient descent or the various forms of it and try to optimize or find optima with respect to some form of objective, right? In black box optimization, on the other hand, we don't assume to have access to either the gradients, or the gradients might simply be ill-behaved and therefore not really suitable to be used with gradient descent-based optimization. Instead, what we assume is that we have access to function evaluations. Okay, so we can query the function, we can get some form of fitness score or some form of performance metric, and then we can adjust samples of x or different x's in order to better our solution. And there are many different black box optimization or zero order optimization methods, including super simple things like random search, but also Bayesian optimization, successive halving, hyperband, and evolutionary optimization. And what I want to sort of pitch today is that evolutionary optimization lies at a sweet spot where it can not only optimize sort of tens or 20 hyperparameters in whatever you're doing, but it can also meta-optimize small or relatively small neural networks that can parametrize entire algorithms. Okay, so think about objective functions or even evolutionary optimizers themselves. Okay, so now let's quickly turn to what an evolution strategy is. So in evolutionary optimization, more generally, there are sort of two big classes of evolutionary optimization methods, namely evolution strategies and genetic algorithms. And an evolution strategy maintains a search distribution, most oftentimes a multivariate Gaussian with some form of sufficient statistics. For example, here we are looking at the mean of this Gaussian distribution as well as a diagonal covariance matrix. And then we can sample from that search distribution different X candidates, right, denoted by these red points. And then we can evaluate them on a task that we're interested in. Like here, it's like this 2D synthetic function, but it could also be like the parameters of a robot that we're just evaluating on some form of continuous control task, right? And then once we have evaluated the set of parameters, we get a set of fitness scores, right? And we're doing so for a population of n population members, where n just denotes the number of points in parameter space that we set. And then given these fitness scores, we can then move the search distribution in this generation towards sort of better performing solutions, right? So the intuition is that the update of the search distribution is going to increase the likelihood of sampling better performing solutions in the next generation. And then we can update or iterate this process each time sampling, evaluating, and updating the search distribution. And again, here, we don't need to have access to any form of gradient. We just need to be able to evaluate the function. So what are challenges of this approach? Why is not everyone doing black box optimization, right? So one sort of fairly obvious challenge is the curse of dimensionality, right? So is the number of parameter scales. We might need more and more samples in order to cover sort of the search space and to be effective in terms of finding a good solution. Another key problem, which is much more pragmatic, is one of engineering, right? So if you do these parallel evaluations, you want to be sort of not have to do the full hardware engineering of getting these parallel evaluations sort of done in parallel, not in sequence, but instead you want to have a form of software kit that does this for you and actually also uses the hardware acceleration that's currently available. Right? So what I'm plotting here is sort of the standard setting where we have workers, like for example, different axes, right? And most of the times we don't only want to evaluate them once, but we want to do this in a Monte Carlo style, right? Where we want to estimate fitnesses not only from one stochastic evaluation, but from multiple ones. And if you sort of follow the standard evolutionary paradigm from a couple of years ago, you would use some form of management tool like Ray or Dask to do so. Right? But this again sort of is oftentimes very hardware dependent and can be buggy at times. So this has led the icon of Jan LeCun to sort of state that gradient-free methods are the devil, or no, are to be avoided at all costs, but sometimes they're sort of a necessary evil that you have to take into account. What I'm sort of pitching today is that modern hardware acceleration and JAX allows you to overcome at least this engineering problem quite efficiently. Okay, so JAX at its core, for many people, might just be yet another automatic differentiation toolbox, but to me, JAX is much more. Right? JAX comes with a set of primitives, grad, JIT, VMAP, and PMAP, that allows you to compose essentially these function transformations in a way that allows you to do large-scale evolution. So grad simply computes the gradient of a function, JIT just-in-time compiles it, VMAP auto-vectorizes it, and PMAP sort of parallelizes it across different devices. Right? And each one of them you can sort of chain together. And so what does that mean for evolution, right? So one thing that you can do with VMAP and PMAP is essentially go ahead and instead of having to have different workers and orchestrate them with like with a manager, you can go ahead and simply use VMAP and PMAP to parallelize these fitness rollouts, right? So what I'm showing here is, for example, one sample that parameterizes a robot policy, and then you would want to evaluate this multiple times. And then you would want to do this for multiple of these samples. And literally you can just chain VMAPs and PMAPs to essentially do all of this robot evaluation in parallel across multiple devices, as many as you have access to, essentially. And this is sort of just one way how evolution can be sped up by using JAX. Another way that I personally find even more exciting is that you can do these same transformations for entire unrolls of learning or evolution rollouts, right? So what I'm showing you here is just sort of this loop that we've seen before, where you sample, evaluate, and update a search distribution in a loop. And you can now go ahead and use a VMAP or PMAP transformation that just essentially does this in parallel multiple times, okay? And it can do so for different settings, right? So the most simple use case might be where you just want to run something for multiple seats in parallel, and you just VMAP and PMAP over it. Or you can also think of having different learning rates or different objective transformations or whatever. And JAX allows you to essentially run different algorithms in parallel at a large scale, right? Cody, go ahead.
Just to clarify, you're talking about like parallel and accelerated. And my sense of what you've talked about so far is that this is sort of solving the parallel problem, but that you still like getting sort of like the sort of proper definition of like accelerated, like running on a GPU would require an environment that can run on a TPU. So just to clarify,
Exactly.
is that like, so is okay. I just wanted to clarify that that wasn't sort of already implied by things you mentioned. So
yeah, so JAX is built on top of XLA, right? And XLA compiles directly to CPU, GPU, or TPU, right? So you as the user, you don't have to take care of that part. It's sort of done by JAX automatically, and it's fairly agnostic thereby to what kind of accelerator you run, right?
Yeah, I mostly just meant that like this imposes a constraint of your environment needs to be able to be simulated on a TPU, which like not all environments currently are designed for.
Exactly, that's entirely true, and this is sort of where sort of this second open source project from me, GymNext, sort of comes into play, which writes essentially classic OpenAI gym environments in JAX natively, so that you can do this. Yeah, but you're completely right. Not everything can be parallelized, but it has to be sort of in this JAX format that allows you to do so. Good, awesome, thank you. Good. So these are sort of two use cases where JAX is helpful for evolution. One is parallelizing population rollouts, and the other is parallelizing entire algorithm rollouts, essentially, right? And for the second one, you can already imagine that this is really nice if you want to do something like Meto-Evolution, where you stack sort of an evolution layer on top, right? Okay. So this brings me now to evosax, which is this library of evolutionary optimization algorithms that I've been maintaining, which implements a set of more than 30 now evolutionary optimization methods in JAX natively. So you can directly execute the search strategy on an accelerator and also parallelize over sort of different instantiations of these search strategies. So now I'm going to turn from the background section to the actual projects, or sort of to the motivation of some of them. So I guess all of us kind of know that throughout the history of machine learning, we've moved from a paradigm where things were manually designed, like for example here, SIFT feature detectors in computer vision, to one where algorithms are discovered or learned, right? For example, in the form of filters in a convnet. But more recently, sort of people have extended this to also discover, for example, objective functions in the context of reinforcement learning, or, and this is what's probably most closely related to what I'm going to present to you, also to discover new optimizers, right? So this is this line of work by Metz, for example, where instead of using Adam and like a fixed equation essentially to perform gradient descent updates, you can have a neural network which receives a gradient as an input in some form of summary statistics and then outputs a weight change. And the weights of this neural network are essentially meta-learned on a set of tasks. Okay. And thereby, essentially, we're discovering directly algorithm components from data and from sort of experience that we can generate. And essentially, Meto-Evolution makes this, or can turn this into like a cookie cutter kind of template for doing discovery of new evolution or new algorithms, right? So what I mean by that is, if you have an algorithm which is parametrized by these meta parameters theta, then you can essentially go ahead and run your inner loop algorithm in parallel, for example, using JAX, and then in an outer loop have an evolutionary optimizer that refines these meta parameters theta across time. Right? So in the outer loop, you would sample different thetas. In the inner loop, you would run that algorithm to refine some form of x. You would evaluate that x at the end, get a fitness score, and then in the outer loop, update these theta parameters which characterize the algorithm in the inner loop. Right? And there, as I already said, sort of many different examples of this. So the work by Metz on remit-based optimization. There's some work where people use this in computational neuroscience to essentially discover new plasticity rules. There's work on sort of discovering RL objectives, for example, by Chris Liu, called Discovered Policy Optimization. There's the idea that instead of training in an environment that's described by sort of equations of physics, you can also try to meta-learn or a synthetic environment characterized by a neural network. Or you can think of trying to discover communication channels between agents where you can either help or manipulate other agents. And there's sort of a fundamental trade-off here between sort of the substrate, which you're trying to optimize in the inner loop, so the theta, or what the theta characterizes, and how easy or hard the optimization is on the outer loop. So for example, if the only meta parameter, like this theta, is only a learning rate, then the meta optimization might be very simple because you're really just tweaking that one parameter. While if you want to discover an entire objective function without a lot of structure in it, then the meta optimization might be harder, but you're also ultimately doing more discovery, right? You're leaving more room for something new to be found in the meta optimization. Okay, so one question that might pop up to some of you is, why should one use Meto-Evolution instead of meta gradients, right? So use something like MAML style computing gradients to gradient update steps. And one reason for doing or for not doing so is that you're essentially tied to propagating gradients through computation graphs. And if you don't do this for a single step, but you do this for multiple steps, then you're running essentially into the same problems that you had with sort of recurrent neural networks in the early stages, where you're essentially having vanishing and exploding gradients because you're computing gradients to these unrolled computation graphs. And here we don't have something like gating in place that can make these sort of optimization dynamics better behave. So let me give you an example of this. This is like a very simple toy example taken from Razan Pashkan's paper from 2013, where he introduced gradient clipping. So what we have here is a simple one-dimensional linear dynamics or nonlinear dynamical system, where there's a variable x, and this variable x is squeezed through a nonlinearity. I think this is a sigmoid multiplied by weights, and we add a bias. And after a set of 50 time steps, we essentially output some form of prediction, y capital T. And the goal essentially here is that at the end of this unroll, this YT should be close to 0.5. And then you try to optimize the weight and the bias just using gradient descent, for example, and you can then plot the entire loss landscape for these two parameters in this plot that I'm showing here, right? And what you can observe is that there is this extreme cliff where essentially if the optimization dynamics somehow arrive here, this is going to jump away and we're going to have a big instability in terms of optimization. And this cliff essentially arises or is more pronounced because we have this unrolled computation graph where things can easily sort of explode and jump away. If you now take an evolutionary approach, you can essentially sort of smoothen out this loss surface that I just showed by applying essentially these random mutations, right? So you just have to trust me here. This is a bit hand wavy, but what this is essentially doing is it's taking a Gaussian filter and sort of pushing it over this landscape, okay? And by doing so, this is obviously becoming more smooth, right? Because the edge is essentially smoothened out by this filter. And if you then do some form of optimization on top of that, this is a lot better behaved. And these are sort of the applications that we're ultimately interested in when doing meta-optimization across longer timescales, not only across 1 or 2 update steps. Okay, so this is the case or the argument for using Meto-Evolution instead of meta gradients in order to sort of overcome or avoid these exploding gradients. Now, I'm going to turn to the 2 papers that I want to present. One of them is on essentially using this idea of meta-evolution now in the context of discovering evolutionary strategies or evolution strategies. This is published at iClear this year. And the other is on using the same sort of setup or cookie cutter template, but now not discovering evolution strategies, but genetic algorithms. And I'm going to get to what the differences are between these 2. And this is published at Gecko this year and even nominated for the Best Paper Award. So if you're at Gecko, which I'm not sure, then please vote for us. This is really important. No, okay, good. So after self-promoting, let's jump into the content. So you remember this background that I gave on evolution strategies, right? Where we have a search distribution with a mean and some form of covariance, and we want to shift that into the direction of the best performing members and do so most effectively. And what many sort of evolutionary optimizers do is use some form of rank transformation of the fitness scores. So imagine you have a population of n population members, and then you have to somehow use them to transform ultimately your mean. One way to do so is to use a fixed rank-based sort of transformation where the best ranking population member gets the highest weight, and then the less well-performing population members get smaller weights, okay? And then you can use these weights together with the evaluations where they're coming from, essentially, to update your mean into that direction, right? So this here is just like a weighted average over different evaluations, and the ones that get sort of the highest weight pull the mean into their direction, right? And the ones that get the highest weight, in turn, are the one that performs sort of best on the task. And this has like a couple of limitations, namely that if you always use this fixed rank transformation, then this is sort of independent on how much these different population members sort of differ, right? So you're not really taking into account all of the information, but you're just taking the rank sort of into account. The other limitation is that these learning rates that you use to update the mean and the standard deviation are usually also assumed to be fixed, and there's not a lot of sort of variation. So what we sort of propose in this learned evolution strategy paper is to replace this rank-based fixed fitness function with a very tiny set transformer, and to meta-evolve sort of the weights of this set transformer on a task distribution that we designed before. Furthermore, what we also do, let me go back. One reason why we use a transformer here is not because transformers are the hot thing to be used, but because they come with a very nice inductive bias, namely of inducing some form of population invariance to the update, okay? So if you use self-attention without any position encoding, then you can essentially get population or some form of input equivariance, where as the inputs change their order, also sort of the outputs change their order in the same way, right? So attention is a form of inductive bias for set operations. And this is for sure helpful in the context of evolutionary optimization, where we are operating on these populations where the actual order of them doesn't really, of the individual members, doesn't really make that much of a difference. So equipped with this inductive bias, we can then try to optimize the weights of the set transformer to give us a type of transformation or fitness transformation that is most suitable for doing sort of evolutionary optimization. Furthermore, we can use different features, right? We don't only have to use like the raw fitness score, but we can also use types of set score transformations or rank transformations in the first place, and use all of them together as input features to the set transformer that then outputs the weights. So you can already imagine there's a lot more flexibility in what kind of function this can represent. And then what we also did is we hooked up like a small multilayer perceptron to control essentially the learning rates of these update equations and to thereby impose some form of schedule as well. Okay, and then we use what I just proposed or talked about, this type of meta-optimization, where we sample weights of these set transformers and perform black box optimization in the inner loop on a set of synthetic functions, run as full search, parallelized and accelerated by JAX, compute a type of meta fitness score which summarizes the performance of these different candidate evolutionary optimizers, and then updates the meta optimizer to essentially improve the performance of what's expected to be sampled in the next generation. Maybe if there are questions at this point, you can raise them. This is sort of a core question.
Yeah, I guess I should have raised my hand. My bad. How many like samples do you need for a thing like this? And just to give a kind of sense of what the compute infrastructure that backs doing this at a scale at which it works.
Yeah. So this is all like reproducible in the context of an academic research environment. So basically, like these meta-evolution experiments, they run on 4 GPUs, I think 4 A100s, and they are in total, I think, something around 5,000 meta parameters to be optimized, population size of like 512, and this is all something that's easily done still in the context of academia. Yeah, also like these tasks here in the inner loop are fairly small scale, so we don't need to have entire sort of training runs of let's say like ImageNet classifiers running in the inner loop. And we're going to see later that even though these tasks are so small, like the meta-evolution process can capture inductive biases, which are really useful for generalization afterwards.
Cool, thank you. Yeah, it's exciting to hear that. Yeah, you just need four A100s and not 1,000
CPU pods. Yeah, I know. Are there any other questions? Okay. Then let me continue. Yeah, like I already said, we're using a small set of synthetic functions. Here, they're coming from the Bebop benchmark. So this is a benchmark from the evolutionary computation community, which consists of 24 of these sort of functions. Here I'm plotting 5 contour plots of 5 of them, and they're sort of chosen to have different sort of characteristics, right? So here in this sphere function is just sort of a convex function where you can solve the problem basically sort of in a coordinate-wise fashion. So these are so-called separable functions. There's something like the Rosenbrock function, which has moderate condition numbers. So this is about the ratio of the smallest and the largest eigenvalue of that function. There's something with high condition number, multimodal structure, and so on. And basically, I'm going to show later that as you sort of increase the number of these functions, you actually get better performance, right? Because the meta optimization process sort of has to incorporate or account for more diverse optimization problems that might occur. Yeah, and then we sample some offsets to make sure that the system is not biased sort of to one optimum location. So many of them have their optimum at 0 naturally, and we run sort of this inner loop search for a small population and a small number of generations. And again, like all of this can be implemented in JAX, right? So that allows us to sort of parallelize all of this. Yeah, and what I'm showing you here are sort of samples from that evolution unroll for the learned evolution strategy, and you can see like that for all of them, like the system quickly optimizes towards the global optimum, which is like the star, and does so in a fairly effective way. And sort of what's worth noting here is that if you just randomly initialize like one of these subtransformers, right, there's nothing saying that it should optimize anything, right? It's just, it would just randomly sample and sort of diffuse over this fitness landscape. And so coming from so this probably just comes from the Meto-Evolution that you do essentially. Okay, and we can look at some form of generalization across the population size and the number of dimensions for like these test functions for these small sort of synthetic functions, and we can see that the system is capable of sort of generalizing across the population size, and as the number of dimensions increases and the problem gets harder, it's capable of sort of combating it by having a larger population, right? So as you have more dimensions, right, the curse of dimensionality kicks in and optimization gets harder, but as you increase the number of resources, it gets easier again, or can do the task. Yeah, Eugene?
I have 2 questions here.
Go for it.
The first is, so I can see on the figure to the bottom right that there is some places where it is outperforming and some places where it's underperforming. And the first question is there a pattern to that? Are there any observable properties about when it will underperform and when it will overperform? And then the second question is, and maybe you'll get to this, is like once you actually look at the thing that is learned, does it have some understandable, interpretable characteristics?
Yeah.
Get to both of those.
2 really good questions. So the second one, I have a dedicated slide for, and I'm going to get there. And the first one, so like for these synthetic functions, I didn't look super close at it, but like for neural network tasks, which we're going to talk about later, I sometimes had that observation that the learned evolution strategy can be more greedy than other evolution strategies, and sort of shows better progress early on. So if you have a small budget, but then has a harder time generalizing for larger sort of time horizons later on, right? And this is part of this is partly due to the meta training being only for 50 generations and not for more, and sort of limited generalization on the time horizon front, right? I looked at certain ways how to get rid of this, but yeah, with all these meta-learned systems, right, you can't always sort of guarantee generalization across every dimension, right? Does that make sense?
Yeah, that makes sense. So the time budget actually kind of sneaks back into the like actual learning algorithm itself, right? It's a little greedy. It knows it has a finite time budget. Something like that is happening there. That's super interesting.
Absolutely, absolutely. And sometimes being greedy is the best thing to do, sort of, or to a certain degree. And sometimes it's too greedy. Yeah.
Yeah. Thank you.
Thank you for asking. Good. So basically, many of these results I already had sort of at the very early on in the internship, and then the question was, hey, how far am I away of scaling this to sort of more interesting tasks, right? And then I just tried taking the system that was meta-trained on these synthetic functions and seeing how well it performed on robotic control tasks, right? So what I'm plotting here is like a subset of the DRAX control suite. So this is basically a JAX-based implementation of environments you would find in Mujuko, right? So there are differences in the physics engine, but like the task descriptions are somewhat similar. And basically when I did this, I found that we were pretty competitive at that point already. And then I did a bit more tuning. And what you can see here are essentially in red, our method and our meta-learned method. And in the other colors, you can see a set of sort of other baselines like competitive evolutionary optimization baselines, including OpenAI, natural evolution strategies, PGPE, and so on. So, like for example, on AND or humanoid or fetch or UF5E, like we're outperforming all of them. And what's interesting here is in the dotted line, we're plotting sort of the converged performance of PPO with like a fairly reasonable large compute budget. And we can see that evolution traditionally can't compete on the sample efficiency dimension, but in terms of sort of asymptotic performance, it can sometimes outperform even reinforcement learning methods. Go for it, Eugene.
Sorry to keep interrupting, and feel free to cut me off at any point. If one question I always have when I see slot like this is, how does this compare on wall clock time?
Yeah,
with similar compute budgets.
Yeah, so with Brax, you can already crank through quite a lot of transitions just by having super many actors, right? And then the hyperparameters have to be tuned differently, but it's still, even with TPU, it's not competitive with reinforcement learning methods.
I mean, it's not a criticism. It always takes time to scale things up, and the reinforcement learning methods have the advantage of tons of optimization.
Yeah. So one thing that's sort of a problem when it comes to sort of these time wall clock considerations is that, like with Brax, like usually when an episode terminates, you have an auto reset, and you can just continue collecting experiences for PPO, for example, right? But with evolution, you have to run the full episode basically, and can't really do this reset in an efficient way, right? And this kind of slows you down in terms of how much you can crank through or how many like effective transitions you can generate for sort of doing evolution.
That's super interesting. That seems like a real open, interesting question.
Definitely.
Yeah, I was just wondering, is there any intuition as to why the variance for the humanoids environment is so large? Like,
I couldn't give you a good answer.
Okay.
I didn't closely look into it.
Okay.
Yeah.
Okay.
Like it could be just one run that failed, right? So this is across, I think, 10 seeds, which blows up the variance. But I'm not sure. I can't tell.
Okay, thank you.
We can also have a look at this in an aggregated picture, right? And here you can see again in red, sort of we are outperforming the baselines here more clearly. And this is like normalized against OpenAI ES, right? So the one is OpenAI ES. And what you can see here is basically after less than half of the compute budget, we're reaching sort of the asymptotic performance of OpenAI ES after 2000 generations. We can then also look at sort of the scaling, right? So remember, there's this capital N, like the population size, and ideally, as we increase that population size and we have more throughput, we also want to perform better. And here again, you can see sort of that our method, the learned evolution strategy, scales really well with sort of the increased compute. And maybe again, what's important is here. We're showing in these dotted lines and these gray dotted vertical lines what was meta trained on, and then what we're generalizing to, like in terms of population size and in terms of number of generations. And we can see that there's already quite some generalization happening across the time horizon and the population size. But as Eugene sort of asked before, like for certain settings, we don't see it as much. Yeah.
To make sure I understand this right-hand graph, you meta-train on a population size of like 8?
60.
Yeah. Cool.
And then we're meta-test. Okay, yeah, awesome.
No, sorry.
Good. So now coming back to sort of this idea of scaling the meta training. So I already said we have these bebop functions, right? And what I'm plotting here now is the performance on these Brax tasks, again aggregated, for different LES meta trained on different settings, right? So this is just using a single bebop function, using 5 bebop functions, using 10 bebop functions. And we can see here is sort of this clear trend that as we meta train on more tasks and more diverse tasks, we essentially get a system that's ultimately better at generalizing downstream to these robotic control tasks. So this plot only shows half the picture. So if you extend this a little bit more on the x-axis, this plateaus. So there are certain limits that you reach, and these are most likely simply due to what kind of function this very small set transform can even like represent, right? So yeah, it's fairly limited still in what it can do. It's not fully black box, since we have these update equations which sort of only allow you to change the weights and the learning rates. But yeah, good. Next up, we're now coming to the question that of what has the system actually discovered, right? So usually for me, like these, I already spoke about this cookie cutter template where you just take some form of parametrized inner loop algorithm, you do evolution in the outer loop, and then in the end you get a new algorithm, which is parametrized, for example, by a neural network with meta-learned weights. But then sort of the interesting scientific element sort of starts where we actually want to see what has been discovered, right? What has been discovered by this optimization process that we as humans could not manually write down. And so one way to do so is just to visually inspect sort of what the system has meta learned. That's essentially what we're doing here. So in this heat plot, we're sort of showing how these recombination weights change over time, and this is cut off. So in total, they're like I think 128 or 256 population members, and we're sort of showing the amount of recombination weight assigned to these individual population members based on their rank. Okay, and what you can see is that there are generations, like for example the first one, or here I think there's like 27 or something, where basically almost all of the weight is given to the best performing member, while there are other generations where like the top 25 are essentially combined into an update. So what this highlights is that the system can sort of flexibly jump from being like a hill climbing algorithm, where it just copies over the best population member, to something that's more like a gradient descent style update, where you essentially average the top performing population member. We then went on to essentially sort of ablate the different components of the learned system, where we can just sort of use fixed learning rates or use like a fixed rank transformation. And we can see that sort of each time when we do so, we lose a bit of performance. Right? So the brown curve here uses fixed learning rates and asymptotically performs as well, almost, but like early on doesn't, while the one with fixed weights sees like a strong drop in performance. So this is like the visual inspection part, but then my co-intern and friend, Chris Liu, he kind of looked at whether or not we can now go ahead and reverse engineer this neural network-based evolution strategy into a closed form equation that captures most of the performance. So in this plot here on the bottom left, we're kind of plotting the impulse response function of this neural network as a function of the ranks, okay, of the population members. And what we can see here is, so the negative rank is essentially, or means that this is like the best performing member, while on the other side we have the worst performing members, since we're doing minimization essentially. And we can see that there's like this nice inverse sigmoid relationship between the centered rank and the weight logit that is being given by the transform. And we can then sort of do like simple logistic regression fitting basically to this, where we get a closed form analytic expression for this transformation that the transformer is otherwise doing with a temperature parameter. And we can then sort of here in this plot over here, rerun all the evaluations on Brax with this closed form expression, where we can tune this temperature parameter to perform well on these different tasks. And we can see that if you do this tuning, we're essentially recovering most, if not almost all, of the performance of the learned transformer-based method. Right? So here, the takeaway is not, well, we didn't even need the transformer, but the takeaway is much more, hey, we could use Meto-Evolution with this flexible transformer-based evolution strategy, and then afterwards distill what has been discovered into something closed form that was previously unknown to the evolutionary computation community. Yeah, go for it.
Is the beta tuned per task, or is it one fixed beta?
Exactly. So here, like, so the fixed beta is like the salmon, I think this is the color, and the gray one is where it's tuned per task.
But it's something you can like tune online. It's not like are you hyperparameter tuning it per task, or is it something that's being tuned online?
I'm hyperparameter tuning it per task. Yeah.
Okay, cool.
So
Thanks.
Yeah, no worries. Good. Yeah. Oh, no. Okay, good. This is basically like the core results of this paper, but something that really got me interested in the beginning into pursuing this direction was reading the diploma thesis of Jürgen Schmidhuber. And already like in the 80s, he thought about systems that self-referentially refine themselves, right? So his diploma thesis was on basically stacking genetic algorithms on top of each other that each sort of change the inner workings of the ones below them, right? And to do so in a self-referential way, you start essentially from a blank slate and then just have some form of fitness super meta objective that kind of guides all of this. And basically, after I had these results that I showed you before, I was wondering whether or not we can do something similar in the context of learned evolution, where we go ahead and we use essentially not a fixed meta optimizer that's some evolution strategy that was previously manually designed, but you use a randomly initialized learned evolution strategy as the meta optimizer that then drives essentially the performance. Okay. So here I'm showing how it looked like before. We have this inner loop, which is LES, and then in the outer loop, we sample tasks, we sample LES parameters, like CMAES or some form of evolutionary optimizer. We run the search in parallel using JAX, and then we perform like a meta update. But now what we're doing is we're essentially adding or replacing the meta optimizer by a randomly initialized version of LES. And then in the meta update, what we're doing is we're looking at whether or not an LES in the inner loop has outperformed all the LESs seen before. And then we use the parameters of that LES to replace the outer loop parameters. Okay. And we do so using some form of hill climbing and resetting of the variance in order to not get stuck in the meta optimization. And here again, like this whole process starts off as completely random search, basically, right? So the LES that is randomly initialized doesn't really know what to do, just samples parameters for the inner loop. And then as you see better performing LESs in the inner loop, you replace the outer loop parameterization and can thereby sort of bootstrap the learning progress that you've seen in the inner loop. And here I'm now showing you the performance of the system for these Brax tasks, again, in an aggregated fashion, where we can see in red sort of the LES that was meta-learned using CMAES, and in blue, we can see the self-referentially meta-learned system, okay? And we can see that it can do the job of performing neuroevolution on Brax. It still doesn't outperform the CMAES based meta-learned system, but at least for the time being, it's hoped that we might end up in a fully open-ended setting where we can drive self-referentially meta-evolution, sort of going forward. Yeah, I have some ideas of why this is not working yet fully, but I can talk about them later. Good. So basically, this was this was the first paper. Now I just quickly want to talk about the second paper, where we apply exactly the same sort of setup now to genetic algorithms. And unlike in evolution strategies, genetic algorithms don't maintain the single search distribution, but they keep an archive of essentially parents, right? So these points here, and then you sample children from them and evaluate these children. And basically, again, based on these fitness scores, you can then go ahead and update the parent archive. Right? So this is a form of selection that's then happening. So you sample children from the parents, you evaluate these children, and if the children outperform their parents or some form of or the parent members in the archive, you refine the archive. And again, you can then go ahead and use a type of meta optimization, where here we define selection and mutation rate adaptation using self and cross attention. And again capture a full new family of potential genetic algorithms. I'm skipping over the technical details. Sort of the main important thing here to take away again is that we can use attention as a inductive bias for set operations in the context of genetic algorithms, and then meta-learn again the parameters of these operators that characterize genetic algorithms. And here, again, I'm just showing you results where in red we have the genetic algorithm on a set of different control tasks. And this is like a hyperparameter optimization benchmark HPOB. And we can see that the system is capable of outperforming the genetic algorithm baselines. It can't outperform evolution strategies necessarily on many of the tasks. But this is something that was already kind of established before. Like, it's very hard for genetic algorithms to be competitive with evolution strategies on many of these tasks. Good. Let me skip this. You can basically also, again, try to do reverse engineering of what this system has meta-learned. And something that's kind of exciting is that you can take these meta-learned operators and you can extract them and plug them into other genetic algorithms. Okay, so basically what I'm showing here on the right-hand side is like a very simple genetic algorithm that inherits from the learned genetic algorithm individual operators, and sort of can capture then a lot of the performance gains that you get from meta-learning, essentially the entire system. Good. Let me quickly summarize what I talked to you about today, and then we can open up for discussion and like the more philosophical outlook again. So basically what I showed you today were two ways how to parametrize black box optimizers using self-retention and cross-attention, one being in the form of evolution strategies, and the other one being in the form of genetic algorithms. We could then crank on basically our Meto-Evolution pipeline to learn the weights of these, and the black box optimizers that came out were capable of outperforming hand-designed or manually designed optimizers. And then finally, what we did is we looked at how we can reverse engineer them into interpretable evolutionary optimizers, and whether or not we can even optimize them in a fully self-referential way. Good. So let me now come back maybe to the very first slide where we looked at the creation of Adam. Many of you may know this concept of survivorship bias. And for those of you who don't know, this sort of story of this airplane that I'm showing you here might be quite illustrative. So basically, the story goes as follows. After the Second World War, a plane returned back home, and this plane had a bunch of holes through it, right? And then the engineers wondered or asked themselves, how can we make the next generation of airplanes even better, right? And for many of us, or at least for me, it would be intuitive in the first moment to think of, hey, what is damaged? We need to reinforce what is damaged, right? What is broken. But it turns out like this plane, like, it returned home, right? So what this basically signals is that all of these holes were not detrimental, right? So the plane could be damaged in all of these places. The places that were really important were essentially the ones which didn't receive holes, right? And to me, sort of now making the jump back to the machine learning world, it feels like we're constantly sort of trying to find new techniques, like, for example, batch norm or skip connections or pre-layer norm, post-layer norm tricks and hacks to make a system work, namely gradient descent, and to fix that system, right? But maybe at some point it's even better to think about things like evolutionary discovery of new tools that might sort of be complementary to gradient descent, and not only to always try to fix what's broken in the first place. Okay, so that's basically why I'm arguing for being a bit more diverse in terms of what we explore, and not all of us just always doing gradient descent-based optimization of large models. And so the final thing I just want to highlight again is that I think that for me, at least as a young researcher, this paper by Sarah Hooker called The Hardware Lottery has been really influential, since it really highlights sort of how much our scientific ideas are tied to or path dependent on the software and the hardware stack that is currently available, right? So the magic ImageNet moment would not have happened if Alex Krzyzewski didn't have the insight that you could use CUDA to program GPUs and to scale training of confidence, right? And for that to happen, CUDA and NVIDIA GPUs had to exist in the first place. And it's pretty trivial to imagine that there are tons of really, really good ideas out there which just don't make it right now because the hardware and the software stack don't support them. Right? And I hope that today, at least to a certain degree, I could sort of pitch or motivate that JAX and acceleration can really help us in sort of developing new evolutionary optimizers. Yeah, now we're at the end of the talk. I'm just going to point again to evosax and also to Gymnax, which is this RL library that allows you to run RL environments on the GPU and is JAX compatible. Thank you very much for your attention. And yeah, I hope now we're a couple less people, but if there are questions or anything, then please go ahead.
I'm just going to pause the recording now.